Okay, and we will talk about this. Right? I think we have a question to link it up very quickly. Now, pre-experimental calculation, which is linked to what we say right now, how much you want to use? Here we go. There are certain things we need to be to know, right? Pre-experimental calculation, a lot of times, especially those with kinetics or volumetric analysis, need to be performed. Okay, we always work with a reasonable maximum threshold value for a variable at the end of the experiment. So what you want to collect, whether it's mass or volume, whatnot, what is the value that you always like to see, which you all know. So for example, titration, you want to have what value? Agar-agar is around 25. Okay, for example, and then you work backwards. So designing it, the titration experiment, for example, okay, here we go. We typically want the titer value from the burette to be around 20-25. All right, why? Too low, let's say it's 15 or 10, it sucks because you have a high percentage error. Yesterday we discussed this already. Too high, then what's the problem? Let's say it's 40 cm cube, 42. Remember, if it's 20-25, usually you don't need to top up the burette. It saves a lot of time. This one you have to top up. Every one you have to top up one more time. And every time I top up, there's an error. Potential error. Make sense? So with that in mind, how we start, we'll fix the eventual volume of the titrant to be used as 20 cm cube. We fix it. And from here, this is what I want to say. Everyone, online, on-site, listen up. Yesterday, I have mentioned this. Today is not day 3. I don't scare me. Today is day 2, right? Remember, I say who is the best person to prepare to do planning experiment? The lab tech. From now onwards, I want you to change your role. Your role is not as a student doing an exam to get the marks. Your role is not the lecturer to impress you they know their chemistry with an experiment. And the result sucks anyway, most of the time. Your role is a lab tech. A lab tech has nothing. The professor, the lecturer say, I want to do an experiment in week 1 with these students. The experiment is called volumetric analysis. The name is called Florence, let's say, which is my letter last time. Florence, prepare, report to me. Give me the procedure. 1 day later, I, being the professor, I want the procedure. Make sense, everyone? So your job, you're the lab tech. You are paid to design experiment, to prepare experiment. Things like that, you won't get wrong. And it's easier. Which you all not taught like that in school, right? This is my letter to me last time. They say you have to think like us, not think as a student. Forget about the marks. Just tell yourself you are the one planning this for an open house for your school. And then you have your primary 6, the kiddies student come in. Don't know what is science. Science they know. Don't know what is chemistry. You have to show them the magic. So you plan the experiment that works. Then you will get the marks. Okay, always think like that. You are the lab tech. So lab tech, you will start by thinking, okay, think what? I want all students to have this titer value. Write this down if you need to. I want all students to have this titer value obtained. I want. This is my aim as an lab tech. Because if it's too much, they later top up, then they break my flask, but the professor will scold me. Break my burette. Make sense? Too little, then we tune the error too big. Then the professor also say bad example. Think about it, make sense? So you start there. Then everything will be easier. Okay? So this is what I want the students to get. Sorry? We fix it so that I can design the experiment. I can then back calculate. We're doing back calculation right now. Okay? And as well as yeah, then they can prepare. If not, they know how much of solute they put in the weighing board and put in the volumetric flask and shake, they won't know what. They have to calculate first. Yes. They are the most skilled chemists around in the whole world. Wow. The lab technician.
Wow, thank you so much.
All right. And the amount of other, but they're the most unappreciated. No glamour one. Lab tech, them poor thing. Okay. Salary is also very high, honest. But they're the most skilled. Amount of other reactant in the conical flask and the amount of other reactant in the conical flask. So I kind of fix this amount. So ladies and gentlemen, I also fix this. So carbonate, right? For example, I fix the carbonate. So I fix the mole of calcium carbonate that I want to use. Ladies and gentlemen, think like that, then we have a chance for planning. For calculation one. Okay? Very easy. It's not as difficult as you think. You just have to think that way, then we find the lab that way. Think about it, you want to prepare titration, right? Correct or not? You want to have a solution, right? Calcium carbonate, whatnot. You need to know how many more calcium carbonate inside there, correct or not? So that you know what, later when you react, what is available. And then after that, you also want to know what is the title value you want for your puree. Yeah, so that later they react, I got 20 cm cube, not too less, not too more, or a plus minus a bit. All right, so all this got to be fixed because these are the two things react, isn't it? The titer means the titrant, reactant B. This is reactant A. Make sense? The analyte. Done. Make sense? Those that are online so far, so good. Understand what I'm saying? Yes? Can, All right, make sense? All right, think like lab tech, Here we go. All right, so here we go. And then we can do what? We can work backwards to deduce the concentration of the titrant required. So then you go and prepare your titrant, your sodium hydroxide one, or in this case, sodium hydroxide. So for example, all right, the amount of sodium hydroxide in the conical flask, this is not the earlier question, right? So this is HCl with sodium hydroxide, okay? So here we go, acid-base reaction. Example, the amount of sodium hydroxide in the conical flask, I want it to be 0.01 in a way, so that what? So that the concentration of HCl, which is the titrant, okay, required for neutralization will then be what? Will then be 0.01, the blue colored, if this is the mole, divided by just now, remember the volume, 20 cm cube. Okay, I should keep these to pink, but the pink and blue is the same. Why? Because the molar ratio is 1:1. Everyone okay? So all this we normally won't write down again because it takes up a lot of space. Because the way they react is 1:1. Make sense? So again, I plan what? I plan in my flux. In terms of mole, I will have only 0.01 mole inside there. Everyone okay? Therefore, through this balanced chemical equation, that's why I say balanced equation come out right at the top. Third or fourth line, right? I know this is the amount of mole that react with it. Can see everyone? Make sense to you? And since I want the title volume, all right, I want the title volume. This is the titrant, right? The titrant, right? Since I want my title volume to be 20 cm cube. Ladies and gentlemen, isn't that divided by your 20 tells you what is the concentration I need to make? Make sense? Done. The lab prepares it. Prepare the HCl titrant. So from there, you then prepare your HCl titrant, which is the standard HCl solution concentration, prepared once again via what? Via a volumetric flask and dilution and whatnot. Done. Another one is whereby you design a gas collection reaction. So usually what? Acid carbonate give you CO2, right? Yes.
And the one very constant, right? The thing is, how do they know in the first place that what is the initial concentration of HCl even before they dilute it?
So I don't get his question, sorry. How do I get this prepared?
You got to prepare that concentration of HCl, right?
0.05 lah. Yeah.
Like, how do you know how much you dilute?
Like how you
how much dilute?
Like how does that get into the first place?
Because the laptop have to buy.
Oh.
When you buy from an X company, it doesn't look like this. Anyway, they'll tell you, okay, this is hydrochloric acid. The purity is 98%, 95%, and the concentration is, let's say, 0.5 mole per dm cube. So what do you do over here? The lab tech, therefore, have to do what? Have to do your C1V1, C2V2.
The dilution.
Yes, dilution formula.
Then you can prepare out 25, right? Prepare out 25, and then you go mix down and you put it.
Then you can prepare, depending on how much you want. Okay, everyone? Can, all right? So same thing, you could be served this. Make sense? Another question. I said, give you this, then okay, blah blah blah. So ting ting ting. Okay, drink water, everyone. Okay, drink.
Oh, wait, I read as
Oh, be careful. Okay, designing gas collection. Given a carbonate and acid reaction, the amount of CO2 evolved can allow us to deduce the amount of carbonate present. Again, this one very important, collection of gas. Our gas range usually what value? 50 cm3, right? Okay, so highlight. Because once you got involved gas collection, you're going to use the gas range. All right, you make sure later you back calculate, make sure your volume count don't exceed it. Too small also no good. Make sense, huh? Because percentage error is not good. Okay? All right, that's it lah. Done. Okay, so from here we can work backwards using the equation and then calculate the maximum amount of carbonate that should be present. Can everyone? All right, using the equation, which is correspond to the maximum mass of sample to be used when you do whatever. Okay, done. General. Okay, this is the one. Not sure whether you know.